So good morning, and thank you for joining us live at the Sydney Opera House. My name is Marisa Cardoso, and I'm from UNSW Science. I'm your MC for this event. Now, while all you can see is me at the moment, let me assure you we're here with girls from more than 30 different schools. So, girls, do you want to make some noise? You see, you're not alone. We are not alone. If you want to know what lonely is, think of the Mars rover Curiosity. It's been on Mars now for just over 5 years. And on its 5th birthday, which was about a week or so ago, it was programmed to sing happy birthday to itself. Now that is alone. But you are not alone. So welcome everyone to your Mars community. There. Here at the Opera House, we stand on land that is not alone either. It's been inhabited longer than most places on Earth. I'd like to acknowledge the Gadigal people of the Eora Nation, on whose land we meet today. I pay my respects to their elders past and present, and also to all Aboriginal and Torres Strait Islander peoples here today. And what a program of speakers we have for you to listen to today. This morning we're going to start at the very beginning and take you underwater. Then we'll bring you up onto land, and then we'll look up to the stars, and then we'll burst into space. So if you're watching online, you're welcome to join us on Slido and to ask questions throughout the talks. There will be a quick Q&A with each speaker after each talk, and then there's a bigger Q&A session at the end. Just remember to include the name of the presenter you would like to direct your question to. So to start off this morning, and to lower it into the sea, it is my great pleasure to introduce Professor Emma Johnston. Professor Johnston is Dean of Science at UNSW Sydney, and she's a leading authority in marine ecology and carries out her research under the sea from Antarctica to the Great Barrier Reef to Sydney Harbour. So would you please welcome Professor Johnston.
Thanks everyone, it's a great pleasure to be here. I love talking about the ocean. I often talk about the ocean as if I'm talking about another planet. And that's because whenever I dive in the ocean, and I've dived in some very strange places, including under the ice in Antarctica, but no matter where I'm diving, even if it's a suburban location like Sydney Harbour, I always feel like I'm opening the door to another world. It's so different. Now, I'm an ecologist. Sometimes I call myself an ecotoxicologist, a biologist, an evolutionary biologist. I delve into a lot of fields of research, but basically I'm trying to work out why animals and plants are where they are under the water. What's driving them to be there? How did they evolve to fit that particular environment? And if we change that environment, as humans do, how are they going to respond? How are they going to survive? Now, one of the best techniques I've found throughout my career for understanding why animals are where they are and why they are the shape they are and why they are behaving the way they are is by imagining myself in that environment. Sometimes by getting in there myself, and sometimes just by imagining all of the differences that exist in marine systems. If life largely evolved in the ocean, then what's it like to be down there? And so for a moment, just for a moment, while we get started, I want you to all do a little exercise with me, and it involves closing your eyes. It's a little bit of trust exercise. So everybody close your eyes. Everybody up here, closing your eyes. I don't want to see a single eyeball. Okay, without opening your eyes, I want you to point to where I am. Good work, you're pointing at the microphones, the speakers. So how did you know where I was? I could have been anywhere. I could have snuck around. I could have snuck out. Does anybody know, obviously, you're using your ears. Why did I do that little exercise? Because underwater, you know? No? That was a rhetorical question. Underwater, sound travels much faster than it does in air because water is much more dense. So a lot of animals use sound instead of eyes. What's another reason for that? Because water absorbs light. So the average depth of the ocean is 4 kilometres. That means the majority of that huge area, 70% of the globe covered in water, average depth of 4 kilometres. Light is pretty much all gone by 200 metres depth. Most of the ocean is pitch black. So what you just experienced is what most marine life experiences for most of their lives. Of course, there is a very brightly lit area, the top 200 metres and pretty much the top 40 or 50 metres, where photosynthesis can take place. And that's the bit that we tend to focus on. But even there, light is dropping out. Is anyone a diver here? Not yet? I highly encourage you to do diving if you ever get a chance. But if you do go diving, and you can do this off the heads of Sydney Harbour, you drop into the water, everything's light, everything's normal, it's a little bit cold. You go deeper and deeper and deeper and deeper and deeper, and all of a sudden the world turns blue. So all of the red lights, the green lights, the yellow lights have been blocked out by the water above, absorbed. And if I cut myself down there, or if one of those lovely bull sharks came and bit my arm off, I would bleed blue. Not because my blood had changed colour, but because the light's different down there. And obviously, if I keep going down, it'll be pitch black. So what else am I feeling? And this is all about understanding. If you understand from your own perspective what it would be like to dive in the ocean, you can understand why animals and plants have evolved to be the way they are. Plants at the top, animals down the bottom. Deep sea animals, not much photosynthesis going on, not much food down there. How have they evolved to adapt to that? Not only have they got huge bulbous eyes to try and capture any light, they can create their own bioluminescence, and they have enormous mouths. Sometimes with the fish that live in the deep sea, their mouths are 8 times as large as their body. And that's because if they are lucky enough for a piece of food to come past, and if it happens to be quite a lot larger than them, they are not going to let it go. They're going to grab it anyway, even if it means they have to spend quite some time trying to get it into the rest of their body. So it's light that's different. It's the cold that's different, because water absolutely has a greater heat capacity than air. So if you jump in the water like I do in Antarctica, I jump in with a dry suit. I don't even touch the water if I can help it. If I jumped in without my dry suit, I would lose limb capacity, the ability to control my limbs within 2 minutes, because water takes away heat from my body 27 times faster than it happens on land. And water in Antarctica is minus 1.85 degrees. It's so salty it doesn't freeze at 0. So it's darker, it's saltier, it's colder, and it's more dense. So if I take a deep sea organism and I bring it up to the surface, it's like jelly. It's just going to flop around. Doesn't look very charismatic at that point. Why is it all floppy? Why, if I bring a giant squid up to the surface, does it not even look like the shape of a squid anymore, but looks like a flat, smooshy thing? Because down in the deep, there is so much pressure that organisms don't have to build the structure that they would up here on land. Up here, we're working against gravity all the time. Down there, they are supported by the pressure from all sides. And so the structural properties of those organisms are very different. I've touched on just a few things about life in the ocean. I explore it personally. If you have any questions about how and why I do that, I'd welcome them. But I'd just like you to take away from this moment that going into the deep sea or going into any of our oceans is like travelling into another world. And while we look to the stars, we should also be looking out to our oceans to see the incredible life that lives there. Thank you very much.
Thank you, Emma. I'd like to open up the floor to some questions. Does anyone have a question for Emma at this stage? Just raise your hand and someone with a microphone will come past.
It's always difficult to ask the first question, isn't it?
It's done that.
Yeah?
I'm just wondering, as a diver, what's your favourite place to dive?
What's my favourite place to dive? Well, I mean, this is a bit mean because not many people get the chance to do it, but my favourite place to dive is Antarctica. Yeah. So one of the reasons that Antarctica is my favourite place to dive is because when you get under the ice sheets can be 4 or 5 metres thick, and so you drill a great big hole through the ice and dive in. Now, obviously, not for claustrophobic people, but once you're in, you are in a marine environment, only 5 to 10 metres deep in the water, but it's as if you've dived into the deep sea. So there are sponges as tall as me, there are anemones as big as baskets. They're all filter feeding because there's no light getting through. So for me, that's incredible, because to get into the deep sea as a diver is impossible, the deep. We physically can't do it. We have to do it in remote operated vehicles. But to get into a pseudo-deep sea in Antarctica is possible. Now, one of the most disturbing things that I study about Antarctica is the changes in the ice sheets. And obviously, with climate change heating the world up, we have some really deep concerns about what will happen to those ice sheets. If those ice sheets start breaking out earlier than they usually do in a season, we could lose those near-shore deep sea communities like that, because they'll be outcompeted by the algae. And that's something that, just one of the many concerns I have for the marine environment in the face of climate change. Yeah. Yes? Oh, sorry. Yep.
So it was previously mentioned that you have gone to the Great Barrier Reef. Do you believe there is any solution for change? Like, I presume you know the scientific knowledge behind the state of Great Barrier Reef.
So that was a great question. Is there any solution for the Great Barrier Reef? And you will have heard quite dramatic stories, and they're true, about 2 global bleaching events, one in 2016, one in 2017. So I sit on the board of the Great Barrier Reef Marine Park Authority, and so I know in great detail what damage those bleaching events have done. Now, there were no mass bleaching events before 1998. Since then, there have been 4. We now predicting under the current climate change models that bleaching events will take place up to every 2 years by 2030. Coral reefs can recover from bleaching events, but it takes about 10 to 15 years to get most of the structure of the reef back. So if there's a bleaching event happening every 2 years, there is no chance for that reef to recover. Now, what we're predicting as a consequence of that is dramatic mass mortality of reefs right the way around the world. It's a very pessimistic prediction, but it's quite an accurate one. What the solutions and the hope that we have for reefs are twofold. One, we need to immediately move to low carbon emissions, preferably zero carbon emissions world. We have technologies to do that. We have means to do that. We just need the political will to put those means into place. That's the first optimistic view and solution. The second thing that can be done, that will happen, is that reefs will move and reefs will evolve. So for every coral reef, for example, the Great Barrier Reef, on average in a major reef area, there'll be 100 different species of coral. And evolution can work very rapidly. So if one of those individuals of one of those species of coral can survive a bleaching event and can reproduce, then its offspring are likely to be more resilient to the higher temperatures. So there will be some species that get through. It won't be the reef as we know it today. Finally, scientists are working on trying to breed super resilient corals. So they're crossbreeding, they're pre-stressing, they're using evolutionary techniques to try and breed uber corals. And for the first time ever, the Great Barrier Reef Marine Park Authority is considering allowing scientists to trial those uber corals on the reef. That's a very different way of managing a reef. In the past, we've tried to protect it from human activities. Now we're moving to intervening because the risks of leaving things go as they are too great. There's a Catalyst episode coming out on that in the next month or so. If you haven't been watching Catalyst, you should. It's started back up again every Tuesday night. Am I allowed to advertise the ABC? Yeah.
Too late now.
Yeah.
Thank you, Emma,
Thank you.
For your talk and answering the questions. There will be time to ask Emma more questions at the end of listening from all of our speakers. I'm now delighted to invite Tara Djokic to bring us all out of the water and onto land and back in time. Tara is a UNSW PhD student and in May this year, Tara was part of a group of UNSW scientists who discovered the oldest fossil evidence of land-based life on Earth in Western Australia. Please welcome Tara to tell us more about discovering early life on Earth.
Thank you. Thank you very much. I never have any luck with slides. Okay.
Okay.
Right, so basically when I was a kid, I literally was one of those kids that used to look up at the sky at night and think, like, what else is out there? And I had no idea. I didn't even know what stars actually were made of, but I was just kind of curious, right? But when I was in high school, I was interested in science, but I actually thought that everything had been discovered, which sounds really bizarre, but that's kind of just the idea that I'd somehow developed. And so I didn't see it as being a career at all. And so I didn't do any science subjects. I didn't do biology, I didn't do chemistry, I didn't do physics. I actually failed maths. So anyway, I left school, and 5 years later, I was doing a whole bunch of odd jobs, and I really was dissatisfied. I was kind of bored with what I was doing, and I didn't really know what I wanted to do with my life, but I wanted to do something interesting. And so I thought, okay, maybe I'll go to uni and do a business degree. You know, maybe I'll start my own business. That seems like a good idea, right? Make some money. And I started looking online at degrees, and I thought, well, what else do universities do? And I found astronomy and astrophysics, and I found medicine, and I thought, I literally sat and looked at these things, and I thought, why not? Why not do astronomy? I was interested in it, why not? I have no idea what I'm going to do with it, but I'm interested. And I applied, and I got in to do a Bachelor of Science, to do astronomy and astrophysics. And in my first semester, I did maths, and I failed miserably. I hadn't picked up a maths book in 5 years. So anyway, I was like, okay, what am I going to do, right? Really, I was in a conundrum. And basically, it was lucky because it just so happened that I was going to New Zealand with my best friend that coming summer. And this is actually Mount Ngarahoe in New Zealand. It's Mount Doom in Lord of the Rings. And it's part of this trail. It's a 17-kilometre hike called the Tongariro Crossing. And I was like, wow, like this looks like another planet. These are some of the formations I saw. So that's the Earth splitting open because of volcanic lava coming out at the surface. And I was like, wow, this is crazy. So basically, I picked up a little rock, and I was like, whoa, look at this. This is like a little piece of lava. This came out of the volcano. I thought, why would I study the planets up there when I can study the one underneath my feet? And I went back to uni that following year, and I changed my whole degree to geology. And so in my second year, I found out about this field called astrobiology, and it's basically the search for life elsewhere other than Earth. And so that actually led me to do postgraduate studies looking at stromatolites in the Pilbara. And stromatolites are basically these rock structures that are built by microorganisms, communities of microorganisms, and these are the oldest fossils on the planet Earth. And they actually dominated the planet for about 3 billion years of Earth's history before complex life evolved. So basically, I met my supervisor. Oops, forget you saw that. I met my supervisor, and he said, I want you to study these stromatolites in the Pilbara. And this is exactly what he said to me. I have this project. I want you to characterize the spatial and temporal relationship between Earth's oldest life and hydrothermal fluids. And I said, I'll take it. And I walked out, and I was like, I have no idea what I'm doing. So I did the project, and it was a really steep learning curve. But over the course of 3 years, I did mapping. I went out foot on ground in the Pilbara, picking up rock samples, taking observations. And what we actually found, and what he actually wanted me to do, was understand what type of environment this early life lived in. And that's basically what we were able to do. So we already had an idea that it was an ancient volcano, but the discoveries that we made showed that life was living in hot springs like this one from Yellowstone National Park, or Rotorua in New Zealand, if anybody's been to the North Island. So these are these hot spring pools on land. They're basically the surface manifestations of volcanic systems. So anyway, we discovered that yes, life 3.5 billion years ago, and these rocks in the Pilbara now, were actually living in hot springs. And guess what? We're looking for life on Mars now, right? But as a search strategy to look for life, we need to try and think, well, where are we actually going to find signs of life? And it just so happens that a lot of the crust of Mars, or the surface of Mars, is about the same age as the early Earth. So if we're going to go look for life, we want to go look for something that we know we would find in early rocks on Earth. And so for me, it's really cool because I was really interested in astronomy. And now my research as a geologist has led me back to look at the planets up in the sky. So for me, it's like a real full circle. And if you asked me 7 years ago, where would you be? What would you do? Is this something that you could see sort of leading you to do a career? I would have just had no idea all this stuff would have happened. And for me, it's really just about following my interests. And that's something that, a lot of people don't do because they get really scared about whether they're going to be successful or not. But honestly, follow your passion, and you don't know where it will lead you, but you probably will get there one day if you just, hang on to that interest. So anyway, that's it for me. That's my whole life story.
Thank you, Tara. Do we have a quick question for Tara? And can I just ask, can you wait for the microphone to come to you? That'll allow our online audience to hear your lovely voice. Any questions?
Is there life on Mars?
I have a question for you, Tara. So in May this year, you went from conducting research in a really remote region to being on the world stage for making an incredible discovery. How did you transition between the two?
Yeah, well, it's definitely a steep learning curve. I've always been really interested in science communication as well, because I think the whole point about doing science is, or the whole point about sort of learning about the world we live in, there's no point knowing about it unless you can share it with people, right? Like, when I do something really cool, I don't want to just be like, great, I did something really cool. I'm not going to be excited until I tell you, and then you're like, wow, that's really cool, and that's like something you can share, right? Because human beings essentially are creatures of community. And so for me, that transition, it was definitely tough. I mean, like even sitting up here in front of you guys, it's quite daunting. Like we're human beings, we have emotions and we get nervous. So for me, it was kind of like, I never really thought that I would make a discovery where people would want to actually hear me talk about it. But given the chance, I'm going to do it. Because then hopefully one day it inspires somebody else to go and do the same thing. Because all too often, a lot of people go through life and they think, oh, I'm not going to do this because I'm not going to be successful. And that is just not the case. We just need to kind of inspire each other. And so making that transition, although it was hard, I think is extraordinarily necessary to push ourselves to do that. I gave a lot of interviews on radio and spoke to a lot of journalists, and I can tell you it was extremely daunting, but fun and exciting. And so that's something, that I would, definitely say comes with being a scientist. If you want to be a scientist, don't be somebody that locks yourself away in a room and doesn't want to share it with other people. Be somebody that wants to inspire other people, because that's what life's really all about. We're curious and we want to share things with each other, right?
Well, thank you, Tara. We have a round of applause for Tara, please.
Do you need that?
Now our next speaker, Kirsten Banks, she stands on the land and looks out up at the stars. Kirsten grew up listening to stories about the great emu in the sky, and today she's studying astrophysics at UNSW. Kirsten is passionate about communicating science, and about a month ago, we made Kirsten's dreams come true, and she got to meet Dr. Neil deGrasse Tyson. Please welcome Kirsten Banks to tell us more about how Indigenous Australians look to the stars.
Thanks, Marisa. Hi there, guys. As you heard, I'm Kirsten Banks. I'm actually an Aboriginal woman from Wiradjuri country, which is known as Central New South Wales. So I come from a place where the sky looks freaking awesome. I'm sure if you look up into the sky tonight in Sydney, it looks kind of, there's some stars there, there's not really much out there. But when I look up to the sky, I can see the Milky Way, I can see this great thing called the emu in the sky. Has anyone heard of the emu in the sky? Yeah, a few people? Awesome. You're awesome. You're all awesome. But like, if people know about the emu in the sky, it gets me really excited because this thing, in Indigenous astronomy, this emu, it tells us things about the land. And a really important concept in Aboriginal astronomy is what is on the land is also in the sky, and vice versa. And an obvious example is the emu in the sky, and also emus on the ground. You know, you can see those things running around. They're kind of terrifying, I'm not going to lie, but you know, you see them on the sky, you see them on the ground. And also with a mirage. Has anyone heard of a mirage before? A few yeses. Okay, cool. So a mirage is like when you can see the sky kind of spilling into the ground. It looks like water on the ground, but it's actually just the sky. So my passion, as you may have noticed, is with the sky. I love astronomy and astrophysics and archaeoastronomy. Now, often, whenever I mention the word archaeoastronomy, people are like, what is that? It's a very new thing that started up only a couple of years ago. But basically, for me, archaeoastronomy is learning about my culture and getting a deeper understanding of how my ancestors 60,000 years ago have looked up to the stars. Basically, in short, I look at the Indigenous knowledge of the cosmic nature of the sky. And so over 60,000 years ago, we are the first people to look up to the stars. We are the first astronomers, and I think that's absolutely fantastic. And to actually learn about these things is really enriching for myself, to learn about my culture and my background, but also just to, I think you can all agree with what's going on in the Earth, on the planet at the moment. Everyone can agree that space is awesome, and that it's very exciting and very intriguing. We all have this curiosity. That's why, you know, we have the Curiosity rover, because we're very curious and we want to learn more. And so with myself, my passions never really moved too far away from the sky. Like when I was young, I was very interested in meteorology, mostly because in primary school, when you're going around the classroom and saying what you want to be, most girls will say, I want to be a vet or a ballerina, and I come out saying, I want to be a meteorologist. Not many kids know what that is, so it sounded pretty cool. As I was going through high school, I was getting more interested in physics and problem solving. And since starting a university degree at UNSW, my passion for astronomy and astrophysics really bloomed and really flourished, especially when I started working at Sydney Observatory, which is just over the water that way. Walking past an Indigenous map, I was thinking, where do I actually come from? Because I didn't actually know what country I came from. So walking past that map, I was able to realize, oh, I come from that country. I come from Wiradjuri. And since then, my archaeoastronomy passion really took hold of me. And now I go through life taking every single opportunity that comes my way, and that's how I've gotten to here today in the Opera House talking to you guys. This is kind of like a peak for me right now. This is really cool. So, but how do you get to where you want to be? Like, does anyone know what their passion is right now? Do you know what you want to do? I see one hand over there. Yeah, go guys. That's okay. If you don't know what your passion is, that's fine. All I want to tell you today is I want to take you to, imagine little me in year 7, first day of high school. My principal is addressing the whole cohort, and I remember it like it was yesterday, mostly because my father reminded me of it yesterday. But I was in that room, and my principal says to me, well, says to all of us, there's a myriad of opportunities out there. All I ask of you is to get off your seats and try them. Try them all. And I took him literally. So I tried everything. I joined the SRC, and I discovered I love talking to people. I joined all of the bands in school and discovered that I love performing. And so here I am performing for you guys. And I even went to all the athletics carnivals, and even though I'm not the most athletic person in the world, I ended up going to zone because no one else was in the race. So there you go. If you try things, like you get experience, you go and do all these things, and one of these things you'll find out that you will enjoy. And then once you find that, grab onto it and keep going, because like all of you guys, you find what you love, and you just keep going for it, and you never let go of it. And yes, it might change, your passion might change, but once you find it and you find your passion, just go for it. Once you have all those opportunities, you can do things like be on national Japanese television, like me. So that's what I want you guys to take away from this. Just try everything. Take me and my principal literally. Do everything. Expose yourself to these things. And then find your passion and take it. Thanks, guys.
Thank you so much, Kirsten. Does anyone have a question for Kirsten? And if so, please raise your hand and just wait for the mic to come to you.
I'm not that scary, guys.
Yeah.
What was it like for you to meet Neil deGrasse Tyson?
Oh my goodness, you should have seen my face. I was like, oh my gosh. I was actually the person who let him through the door to some students like you guys. I'm like, okay, he's on the other side of the door. Oh my goodness, all right. Welcome everyone, and here comes the man, the legend, Neil deGrasse Tyson, and he walks past and he's like, I like your shirt. Like, oh my God. You like my shirt? That's amazing. So, but like meeting someone like that, because he's a science communicator, right? And that's what I want to do. I want to talk to people about my passion, because, you know, as you can see, I love doing it. And to see someone like him who does that, I was like, I want to be you. You're really cool. So it was amazing, in short.
I will point out, she was wearing a UNSW Science T-shirt
Yes.
at the time, and he's a pretty amazing man. Right, so we've heard about life under the ocean. We've travelled back in time and to find the earlier evidence of life on Earth. We've stood on the ground and looked out to the stars, and now our next speaker is going to take us beyond that and out into space. So our final speaker this morning, Solange, is an engineering student at UNSW and co-founder of Cuberider, a STEM education program that brings access to space to the classroom. Today, Solange is here to take us all into space. Welcome, Solange.
Thank you. Can I just get a show of hands? How many of you know of SpaceX, the rocket company? How many of you noticed that just this week in National Science Week in Australia, timing is amazing, that a SpaceX rocket went up to the International Space Station? Hands up anyone who saw that. So on that rocket was around 2,000 of my students, Aussie high school students, your age, and their experiments going up to the International Space Station, which is pretty freaking amazing. Our students are our students are the first Australians to ever send anything up to the International Space Station. We're the only Australian involvement in the International Space Station. So last year on December 9th, on a Japanese rocket, we launched the very first Australian payload to ever go to the International Space Station, with around 1,000 students' experiments from around Australia, from regional, from all across Sydney, from all different states, from year 7 all the way through to year 11. This year, however, we had even some primary school students involved in our program, coding for the International Space Station. But in order to do that, because Australia's never had anything to do with that at all, we had to get approval from 16 other countries. 16 countries and NASA's and ESA's and JAXA's had to approve us. And the first thing they ask is, what government body are you coming from? What research facility are you coming from? And we had to explain to them that actually the pioneering space scientists of Australia are a bunch of teenagers who are learning to code for the very first time. And I think that's something that we should all celebrate, and you all being here today shows that you're all interested in science, and that you should all be, proud to be a part of that big movement that we're going through as a country. And soon we may have our own, space agency and a pathway into that. So I came from, also not Sydney, from about 700 kilometres north, just out of town of Grafton, from a property where I had no power or water or internet or postal service or any of the small things that you get to enjoy just as everyday life commodities here. But I was truly, truly inspired by the night sky above me. I'm fortunate to live in a black zone for light pollution. And that led me to really want to pursue, at first, astrophysics. I was a 5-year-old who had no idea what astrophysics was. But that's what I was going to do. I was definitely going to do that. But then growing up on this farm and like making and breaking things and using power tools, way too young. I developed a knack and a desire to be an engineer. So I married my love of the night sky to my joy of making and breaking things and putting it all back together. And I decided when I was around your age that I was going to be an aerospace engineer. Now, where I come from, that wasn't a thing. Like, it's not really that common to go to university at all, but there were absolutely no aerospace engineers to be heard of in Grafton. And so I had to kind of, guide myself down that route. And I was actually very, very fortunate to have some really supportive teachers in my school who, for one reason or another, they might have been just as crazy as me, I don't know, but they just believed me. When I said I was going to be an aerospace engineer, they were like, okay, cool, right. I don't know what that is, but what do you need to do to get there? And we'll just do it and we'll make it happen. And it turns out some of the people who I thank them most for, being the only Australian to have ever launched anything to the International Space Station are actually not even some of my STEM teachers, but just some really supportive teachers within my school community. I did 5 years of distance education because my school couldn't offer all the subjects I needed to do. And my distance education coordinator is actually one of the few people who I will always thank for their support in that journey. So that's one of my biggest things, is look for the supporters. Have a crazy goal. Doesn't have to be your life goal. Goals change all the time, but have a purpose to what you're doing. I was going to work for NASA. Nobody was going to stop me. That's now changed because I work with NASA, not for them. But that's okay. It's okay for that to change. But the only reason why I got to be doing that was because I had a purpose. That purpose evolves, but I was still driven in a direction that was meaningful. So it didn't matter where I ended up. It was going to be something more positive than if I'd had nothing. And find someone in your school community that believes in you. And by the sounds of it, you've all come here with teachers who are willing to sign how many risk assessments? 400? 400 risk assessments? That's a lot. The teacher that brought you here today is probably that person. Tell them your wacky idea and your dream and what you want to go and achieve, and convince them that you're going to do it, and then get them to back you. And that's basically it for me.
Thank you, Solange. We have time for probably one quick question with Solange, and then we'll move on to the main Q&A session. Does anyone have a question? Again, raise your hand and we'll bring a mic to you. Here we go.
What challenges did you face in launching the stuff from the Australian students to the International Space Station?
Yeah, all right. Well, launching stuff into space, lots of challenges. Countless challenges. Let's see. We had to go through the whole rigor of getting approved to go up there, which, interestingly enough, so I was studying aerospace engineering and maths, and some of the biggest challenges for me were having to understand all the international law that's involved with sending anything into space, and kind of having to figure out. Because Australia hasn't signed all of the treaties involved with the International Space Station, but we've signed some of these other international treaties around space, how we were going to work those different treaties together to make it so that Australians can still be involved in the International Space Station. So I kind of had to teach myself international law along there to get that happening. And that's kind of one of the many challenges of doing it. Yeah.
Thank you, Solange. And thank you to all our speakers. I'd now like to hand the floor over to you guys here in the Opera House and to anyone online who would like to ask our panel a question. If you can just let us know who you'd like to direct your question to, or if you want to direct it to the whole panel, that's fine too. It just helps us in that way. So if you've got a question, just raise your hand and we'll bring a microphone to you. And online, tap away on Slido and submit your question. Here in the front row.
Hi, this is for Professor Johnston, was it? Yeah, so like in places like the Mariana Trench, which is basically untouched by humans, how is climate change, which is like a very human, like a man-made problem, how is that impacting like deep sea marine life down there?
Sure. So climate change is influencing absolutely every point on Earth, but in different ways. And one of the big challenges we have as scientists is modelling and predicting how those changes will take place, because the Earth atmosphere, the ocean atmosphere interactions are very complex. So at the University of New South Wales, in my science faculty, we have a whole centre of climate modellers, and about half of them are actually ocean modellers, because unless you understand the interactions between the ocean and the climate, then you can't predict what's going to happen. So, for example, some of them are predicting how ocean currents are changing as the waters warm. And the currents are essentially controlling our climate because they're these big circulations. At the moment, the ocean has been absorbing a lot of the additional heat that's going into the globe. If it hadn't been doing that, we'd already have gone up 35 degrees instead of 0.8 of a degree around the climate. So as the ocean has absorbed all that water, remember I said it has a massive heat capacity, so it's got a great capacity to absorb heat. It's changing the rate of the current flows, and it's changing the direction and the location of those current flows. That has incredible influence on the climate. In the Mariana Trench, for example, that's got very old, deep, cold water, on average about 4 degrees at the bottom of the ocean. And those waters, we know, are changing in the strength of their flow and very slightly in their salinity and temperature. The other thing we know about the Mariana Trench in the way that it's being influenced by humans is that it actually has contamination down there. So there are PCBs, there are organic contaminants that have entered the ocean through the atmosphere that can actually now be traced in locations like that. So we are everywhere as humans. Our fingerprint is everywhere, even as far as the deep sea. The changes that we see in the deep sea right now are around temperature, around acidity. So the ocean is acidifying. That means as we add carbon dioxide in the atmosphere and it then absorbs into the ocean becomes slightly more acidic. And that's also changing biology of organisms, because organisms rely on a very interesting balance. They're essentially in a soup of chemicals. And that soup is influencing their entire life. Depending on how complex they are, they might be able to deal with a bit of a change in acidity. So, example, fish are quite complex organisms. They have detox mechanisms like we do as humans. But some other organisms are really relying on just the ocean staying really stable, and they're letting substances go across their membranes to and fro in a less regulated way, and they don't have livers and they don't have detox mechanisms. And when they try and do something like calcify, so for example, if they want to build their skeleton out of calcium, so all of the corals do that, or if they want to build their outer skeleton out of something with calcium embedded in it, it's like most of the crustaceans, they need the pH of the ocean to remain really stable. As it changes, it becomes much harder for them to build their skeletons, whether inner or outer. And so what we're seeing in the ocean is really rapid changes in pH, which is happening right the way through the ocean, even into the deep sea, and that's changing organisms' ability to build their bodies.
Thank you, Emma. Do we have any more questions? Up there on the stairs?
I was just wondering, have you experienced any sort of discrimination, especially for people studying like engineering and physics, because you're a woman?
I'll open that up to the panel. Anyone want to take that one on?
I found the environment to be very supportive. And a lot of my mentors in the field, you know, that they describe experiences where they felt it. And I've been very fortunate to be highly supported in my field, both by my male peers and my professors. My general feeling is that everyone kind of recognises some of the issues, and are quite proactive in making sure that, you know, those issues, you know, don't stop and don't affect any more people. As young women who are curious in the field, I wouldn't let those stories deter you from going into it. Definitely at UNSW and some of the other leading universities who I've got friends at, it's a very supportive environment. And if things happen, then there is also mechanisms to help people through that as well. Not that I've ever experienced it or I know anyone that has, but it's a wonderful place to be, and it's only getting better as far as I'm concerned.
Yeah, I think so. I really agree with that too. I remember speaking just last weekend about this. I got a very similar question, being like, how do you go through these barriers of being the only girl in your physics class, maybe? Like I was the only girl in my physics class. And I'll tell you what, that empowered me. Like, yeah, I'm the girl here and I'm doing better than all you males. So it just let that empower you and let it really drive you to do this sort of stuff. Like, no matter what gender, like you do what you do because you love what you do. And that's the main part you really need to think about, I think.
Yeah, and people will see your passion as well, and they will want you to succeed because you're interested in what you're doing. The field of science now is very different than it probably was 50 years ago, and there's a lot of things that are put in place. I mean, I went to a conference that was all about women in astronomy, and there are all of these issues in terms of gender, what was gender bias, being very much decimated. Because people are realizing that doesn't mark your intelligence. And there are a lot of, you know, good people from all different minorities that bring a lot to the table, because science doesn't see any of that stuff, right? It just sees what we want to understand about the world that we live in. So science is extremely proactive in that sense, especially in Australia. So don't let that hold you back, I guess, is what we're saying. Yeah.
Same goes for engineering.
Yeah, and geology. Yeah.
So one thing I would add to that is that girls tend to hold themselves up to higher standards in maths and physics and chemistry than their male counterparts. So unless they're getting 90% or 95% or 99%, they're like, oh, I'm terrible at this. Whereas the blokes, they'll be getting 60% and go, yeah, did really well, that was great, yeah, fine. And so what we need is a little bit of reality check on both sides. The boys could do a bit better. And the girls could relax a little bit and just enjoy their subjects and be aware that if you're still, you know, doing reasonably well, that's great. We still want you in science. You know, we want people who are all-rounders in science, who can do a little bit of maths, a little bit of chemistry, a little bit of physics, a little bit of biology, and a lot of communication. You know, we need people who are great at communicating. We need people who can interact with law and the arts. And so I think not excluding yourself because you're not, you know, that super nerdy 99.9% person, just letting yourself enjoy and be good at science as an all-rounder is a really important thing to keep with you when times do get tough and when you're starting to doubt yourself.
Yeah.
And can I add, this conference I went to for women in astronomy actually mentioned that men generally I'm going to try and simplify this as much as possible, but it's found that men generally are better at like kind of faking it till they make it. So they might be like at a lower level, but they'll go in and be like, yep, no, I can do this. Whereas women might be at kind of like a higher level in terms of, I don't know, grades or whatever, but are a little bit more kind of subdued and not sure of themselves. So when you walk into anything, like have confidence in yourself and don't compare yourself to other people. And even if you think the task might be harder than what it is, don't worry about it. Like wing it, fake it till you make it. Don't think that you can't do it because you haven't tried it yet. So anyway, that was something that I found really interesting, and maybe that's something to do with social structure or something like that. I don't know, but don't let that, you know, bring you down in terms of confidence. Like go in there and be like, I got this, because people will then think that you got it, even if you might not yet.
Thank you. We have a question, I believe, from Slido. Scarlett, do you want to read out the question?
Yes. We have a question from an online audience. Her name is Kylie. She has this question for the panel. Communicating science is essential for modern scientists. Have you received training or support to ensure you can do so effectively?
Fake it till you make it.
Yeah, pretty much. Actually, I remember meeting Neil deGrasse Tyson, and he said to me, think about what your audience is thinking. Try and get inside their heads and try and explain it, not so much using big, redonkulous words like that one. Just try and explain it to like a 5-year-old. If you can explain, you know, maybe slingshotting around the moon to get to Mars by, you know, using little words, then great. If you can communicate science to a 5-year-old, you've got it. Because most people don't know a lot much more than a 5-year-old in, like, say, archaeoastronomy, for example. Not even I do. I'm still researching. So, yeah, explain it in, like, little terms, and that will help.
But also, like, if you feel you're not getting support and stuff, go out and get it as well. Like, when I've asked for it, I've received it. And people don't necessarily know that you need support. Like, you might get, for example, you get thrown into doing something. Like, we wrote a paper, and then all of a sudden I'm getting all these calls about media wanting to talk about our discoveries this year. And, you can't anticipate stuff like that to happen necessarily. So the support network may not necessarily know that you need that. So don't be afraid to then ask for help, because eventually you will find what you need to know in order to tackle that.
I would say that the principles of communication really much play out across the different fields. So some people do specialise in science communication, and they are really important for us. Professional journalists and science communicators are really important, and I think we need people to go into that field specially. But we also need scientists in general just to be communicating their science, as we have done this morning, on an everyday basis. And so the talents that you develop in high school when you do your presentations in any single one of your subjects, and when you learn about listening and being aware of who your audience is, which is what you just picked up, when you realise that using plain English is actually just as effective at communicating as trying to use your fancy words and intimidating people. When you pick up those principles, they apply across the board, and you can use them. One of the tricks that I do a lot of science communication I never thought I would, including on television. And this is just a hot tip in case you're on television, girls, okay? You've got to look at the camera or look to the audience and think about that camera as being someone who would really like to hear your story. So, for example, sometimes I think the camera is my mother, because I know that no matter what I told her, she'd probably be rapt, That really great, And so I can be warm, I can be enthusiastic, and I can get rid of the terminology which is too complicated, and I can speak directly to a camera and not feel intimidated. And I think if you're doing that, no matter what principle, no matter who you're speaking to, if you're speaking to them with warmth, with a genuineness to you, with your own individual shining through, then you'll connect with the people.
Thank you. Do we have some more questions there? One at the back here.
I have a question for Tara, which is probably one of the questions you will be asked in this meeting. So how far is the latest research on life on Mars? How far have we gone? Did we find anything?
Well, I don't work for NASA yet, so I don't have inside information. So basically, there's been 4 rovers on Mars, and they have been looking for life on Mars, since NASA sent the first rover, which is Sojourner, this little one, Pathfinder. But the main objective for a lot of those was just to explore, and there is another rover going in 2020. It's called Mars 2020, and
We're really good at naming things in science.
they'll eventually call it Hope or something. So Curiosity is the one that's taking most of the data, and that we hear from of late. And Curiosity is about the size of a Jeep. It's got all these different instruments on it, And they've been looking for signs of life, but also exploring the planet. But this next rover will actually, one of the primary objectives is to search for signs of life. And in fact, they still haven't chosen a landing site. So, and just to quickly answer the question, no, we haven't found signs of life on Mars yet. The types of signs that we're looking for are past life, the stuff like we see in the Pilbara, stromatolites, microorganisms, because Mars, essentially the geology of Mars didn't kind of like take off like it did here on Earth. So you can imagine Mars and Earth were quite similar to begin with. Earth became dynamic, plate tectonics, took off, evolution occurred. Mars may have formed life, but then it didn't kind of go in the same direction for a number of reasons. We can talk about it later if you like. But basically, if life did evolve, it was probably microbial, and so if we were looking for signs of life, it would be microbial life. And that's exactly what they're basically doing. But in terms of search strategies, so right now they have narrowed it down to 3 different sites that they want to go to. So it's basically been a couple of years, a couple of different conferences that they put together to narrow down. So they started with 20 different sites, so all different types of environments, and all the NASA scientists would do their research and say, hey, we should go here because of X, Y, and Z. And these are the kinds of biosignatures. So biosignatures being, fossils or whatever that will indicate biological activity that we might find at these locations. They've narrowed it down to 3. One of those sites is a hot spring type setting, right? So I'm like, well, we find textures in fossil hot springs on early Earth. Why not go there? The other 2 are like fluvial environments, like lake deltas and stuff, and they want to look for organic molecules, which I don't think they'll find. But anyway, yeah. So the primary objective, though, of this rover is to go and look for signs of life. Now, they will, narrow down that last site over the course of the next year and a half or something like that. But we may still not find out for another, couple of decades potentially, for 2 reasons. One, even if we were to find signs of life in one of these environments, there's a lot of skepticism when it comes to looking at fossils, even in the geological record on Earth. So the real, way that we can sort of nut that down, or bolt that down, is bringing samples back to Earth, and that's probably not going to happen for a while. So maybe we will see textures that indicate life. Maybe we'll see, stromatolites, but there's still going to be a huge level of skepticism as well. But where it stands now, the possibility that life evolved on Mars, I think, is probably pretty high. It had liquid water running on it. It had volcanoes. It had a heat source. Could have had hot springs. On early Earth, we see hot springs with signs of life. And so, then to go, I don't want to go on too much of a tangent, but basically, you guys have probably heard that the theory that life started in deep sea hydrothermal vents, maybe? No? Yeah? Sort of? There's 2 competing theories, which neither has been proven. One is life starting in deep sea hydrothermal vents. Yes. The other is on land in hot springs. And so, so anyway, look, I'm not a biochemist, but I got some friends, and they told me some stuff. So basically, it is now, a lot of evidence is pointing towards hot springs on land. So all you need is some water on the surface, some heat, and these hot springs to form. And we do see environments that are indicated like that on Mars. So if life started on Earth in hot springs, and we see those types of environments on Mars, then potentially, yes, microbial life at least will be preserved there. And we know it's preserved here on Earth. So that was the longest-winded answer ever, but yeah, I'm hopeful. So it'll be really interesting. Keep an eye out. The next Mars rover is going to be launched in 2020. We'll probably get there 2021 or something like that.
That's the European one, isn't it?
There's 2. So I forget the European one, ExoMars.
Yeah.
Yeah, so ExoMars is being sent by the European Space Agency, and then NASA's sending the Mars 2020 rover, which they haven't named yet. But I'm sure someone
I think
will name
Hope
it.
is a good name.
Hope is a good name, yeah.
That's a good name.
So yeah, keep an eye out for that, because this is the first rover to be sent, and the primary objective is to actually look for life. That hasn't been done before. So maybe we will find out.
So
I'm going to
in short,
now.
maybe.
I think we have time for just one more quick question. Great, we have someone in the front row here. Can someone bring her a mic? Thank you.
For Professor Emma, is there actually any way for climate change to actually benefit the ocean?
Ooh, really good question. So costs and benefits are all value judgments, really, and a lot of the time we judge it based on what's good for humans. So from a human service perspective, we rely on the oceans for productivity, we rely on them to take the heat out of the air so that we don't all boil, and we rely on them for fish, we rely on them for transport, etc. There's a whole range of human services that we get out of the ocean. Now, if you heat up certain parts of the ocean a little bit, you could actually get higher productivity. So more algae growing, more microalgae growing, more fish eating, zooplankton eating the microalgae, fish eating the zooplankton, and higher productivity of fish. And that could be a good thing. Whether or not geoengineering or trying to change the climate deliberately is a good idea, we do it a lot anyway. We've transformed most of the Earth's surface into agricultural surfaces or rangelands, for example, in Australia. So we do that a lot, and you could argue, okay, well, we're just going to heat up the land a little bit, we'll get a bit of extra productivity, we'll get a bit of extra productivity from the ocean. What's pretty clear right now is that the climate's changing much, much faster, and the projections are such a substantial change over such a short amount of time that throughout geological history, we don't have an analogue. We can't predict what's going to happen because we can't see back into the past to times when things have changed that quickly. Sure, sea levels have gone up and down. We've had ice ages before. But those sorts of changes have happened over thousands of years. And what we're talking about is the same amount of change happening over hundreds of years. And what we expect is that that's going to be an enormous challenge for organisms to keep up. So the rate of change and the extent of change is what's scaring most people, to say that even if we do get slight benefits in some places, they will soon be wiped out because the organisms won't be able to evolve rapidly enough to keep up with the pace of change. But it's a really good question.
Thank you, Emma. And thank you to our wonderful panel. Can we get one last round of applause, please? Now, before we finish, I'd just like to say a huge thank you to the Sydney Opera House, Inspiring Australia, the Big Questions Institute, the Sydney Science Festival, and UNSW Science for making this event happen. Please join us online again this afternoon at 1:30. Thank you.